Hello, everyone. Welcome to our live session for today, August 8th, 2024. We are happy to be here with you. My name is Matthew. I'm one of the course instructors for our online classes. I also do a lot of the behind-the-scenes stuff here for education and streaming. We are excited to be here with you today. We have, let's see, a bunch of people with us here already. And the way that this stream works is that you post your questions in the chat, and I will grab the questions from there. We go through them to make sure that they are at a level that's appropriate for kind of a beginner, broad audience. So if you have really technical questions, this is not the venue for that. So we try to keep it at a beginner level. And I do see all of the questions. We try to give everybody who wants to ask a question a chance to get their question heard, and then we'll go back through. So I generally try to go in order, but I do sometimes jump around depending on the person and the topics, so we can get a variety of people and topics covered. Chris, why don't you welcome everyone, and then we will get started with questions from our participants.
Right, welcome everyone to the live session, a Q&A session for our MOOC participants or anyone who happens upon this channel. And the floor is open for questions about any topic in astronomy.
Excellent. Well, we will get right to it today. Young Astronomical Research Center asks, do you think science and religion can coexist in the future? Would science be affected by a new science-based religion in a positive way or negative?
There are different perspectives on science and religion. In the United States, in some instances, they seem to be in conflict, but that's mostly in the hands of sort of fundamentalist Christians who question the age of the Earth and are sort of against some very core scientific principles. More generally, science and religion don't have to be in conflict. And I work routinely with Jesuit astronomers and Buddhist monks who come from very different traditions, but are very science-minded and look at evidence and judge things based on that. So I don't think it's anything a given that science and religion will be in conflict. As science progresses, though, it's driven by evidence, it's driven by data, and it doesn't really accommodate or acknowledge the demands of religion. And for Lally, the best way to say it is that science is based on reason and religion is based on faith, and those are sort of different aspects of human experience.
Excellent. The next question is from DS, who is on with us live, and the question is the science behind the explanation of dark matter mere speculation? Is speculating a useful tool in astronomy?
Sometimes you have to speculate because you just don't have enough information, and speculation is not done sort of randomly or without being tethered in physical principles. So the speculation about dark matter is not unbounded, it's not wild speculation. It's based on what could plausibly be a mass component of the universe that dominates the normal material that we're all made of, the protons and neutrons and electrons of normal matter. And there's only so many possibilities. So the speculations about dark matter center usually on a new subatomic fundamental particle, which would represent an extension of fundamental physics, but not an implausible one. Another way to go for dark matter is to alter the theory of gravity and then essentially avoid the need for dark matter. And that's also possible because we don't necessarily believe general relativity is the final theory of gravity. So in each case, the speculation, given that we don't know the answer to this conundrum of the universe, is reasonable and physically motivated, and it tends to be pushing or extending existing physical theories. Dark matter is a new ingredient of the universe. It's not part of the standard model of physics, and so in that sense we do have to extend our theories.
Excellent, thank you. The next question is from Anthony Moore, who asks if you could explain the ultraviolet divergences.
So this is a phenomenon that led to the development of quantum theory in the early 20th century. The ultraviolet divergence is if you calculate the radiation in an enclosed space. Physicists would call this a black body, where you have a cavity and it has a particular temperature. If you use standard classical physics theory to calculate the modes of energy in that cavity with a fixed temperature, you end up with a divergence, because as you integrate the modes of energy, there are more and more short wavelength and therefore higher energy modes, and so it's a divergent amount of energy in classical theory. And that clearly can't be true. That kind of a divergence or an infinite amount of energy in an obviously finite physical situation makes no sense. And quantum theory actually was needed to get around this problem, this ultraviolet divergence. So in quantum theory, the energy scale is not a continuum, it's a quantized scale, because energy can only be exchanged, created or destroyed in finite packets called quanta. And once you impose a quantum nature to radiation, then the ultraviolet divergence goes away, and this problem was essentially solved early in the 20th century.
So we'll jump ahead to a question that is related. So Eric Autumn asks, what is quantum gravity? Is that the same as gravitons?
Not necessarily. A graviton is the hypothetical particle that carries the gravity force, and so that's framing gravity in terms of conventional particle physics, where there's the photon that carries the electromagnetic force, there are gluons which carry the strong nuclear force, there are bosons, the W and Z bosons, that carry the weak force in the nucleus, responsible for radioactivity. And so we have particles or exchange particles that carry the fundamental forces. And so it's just a simple extension to posit or hypothesize a graviton to carry gravity. Nobody's ever observed a graviton, and actually it would be very hard to detect even in principle. So it's not clear if that idea has any kind of traction. So I'm sort of answering these questions separately. That's a graviton, which has never been observed, but is a plausible construct out of conventional particle physics. Quantum gravity is something different. Quantum gravity is an extension of standard physics, because we do not have a physical theory that unifies the two profound and successful separate theories, our theory of gravity, general relativity, and our theory of microscopic matter, the quantum theory. They are each very effective and extremely successful in their own realm, one on the very small scales of matter and the other on the very large scales in the universe of gravity. But the theory does not bring them together. There's no theory that brings them together. So quantum gravity is a phrasing, as a framework, if you like, conceptually for unifying quantum theory and gravity theory. And there are different ways to do this. String theory is one way, which has been worked on for almost half a century now without dramatic success. But there are various other quantized gravity theories. There's a whole little raft of theories, and there are probably 100 or 200 researchers around the world that are working on this. None has yet succeeded in coming up with a unified theory of gravity and quantum theory, quantum gravity theory if you like. So this is work in progress.
Excellent, thank you. The next question is from Kendra Smith, who's on with us live, who asks, if we change the present order of the planets or removed a planet, would it have significant effects on the Earth?
Yes, movements of the planets in the solar system, which are in more or less stable orbits. You can use supercomputers to calculate forward the orbital properties of the planets and run them, thousands or millions of revolutions forward, and they don't really change positions. They're pretty long-term stable. But if you change something, the system can become unstable. I mean, the distances between the planets are huge compared to their sizes, so it seems like the solar system is mostly empty space, and it is. But gravity is a long-range force, and subtle gravitational effects between the planets essentially add up over time as they move in their orbits. So if you move one of the planets, hypothetically, to closer to the other planets, say Mars, you move it in closer to the Earth. It's 50% further away from the Sun than the Earth. Say you moved it by 10 or 20% closer to the Sun. That would perturb the Earth in its orbit and would be long-term unstable. So people have played these hypothetical experiments because you can do them in a computer. And indeed, if you change the parameters of the solar system by not even dramatic amounts, you often render a situation where the system becomes unstable, and the result of that is often that one or more planets are actually ejected from their circular orbits.
The next question is from Ganga, who asks, if the Andromeda and Milky Way collided, what would be the reason behind it? The universe is expanding, so the galaxies are supposed to go away from each other, right?
That's right. The cosmic expansion discovered by Hubble in the 1920s applies to the universe as a whole. And it applies on large scales, on scales of tens or hundreds of millions of light years. Within the universe, on small scales, it's possible for the gravity between two galaxies or two or more galaxies to overcome the cosmic expansion. And that's what's happened in the case of the Milky Way and Andromeda. They're both members of what's called the local group of galaxies, which has those two large galaxies and a few medium-sized galaxies like M33 and a few dozen dwarf galaxies. And the local group is not expanding. And in fact, Andromeda is moving towards us at about 100 kilometers per second. And that's essentially just because the gravity, the mutual gravity of those two massive galaxies is enough to pull them together despite the larger scale cosmic expansion. And the same is true of clusters and superclusters of galaxies through the universe. They maintain their structural integrity and are held together gravitationally, even though on the larger scales the universe is expanding.
The next question is from Chef Senior, who asks, what is the definition of a solar system in astronomy? How far does it extend?
So now that we know there are many exoplanets, that essentially every star has planets, not just the sun, we have to generalize our idea of solar system. So solar system with capital S's is used to designate our solar system, the sun, the Earth, the Moon, and the other planets. And solar system with small s's designates other solar systems elsewhere, and we found many of them. It's not just that there are over 7,000 exoplanets that have been discovered, but there are hundreds of systems with multiple planets. There are even a couple of systems that have as many planets as our solar system does. So solar systems are abundant. They're just as rich in planets as our solar system is, and we're still learning the diversity of properties of the other solar systems in the universe.
The next question is from Geert Steenkamp, who asks, is a black hole a hole or a sphere?
Both. A black hole is more or less spherical because it forms by spherical gravitational collapse of a massive object. But because the black hole, the object that formed it, is spinning, the black holes are almost always spinning in the universe. And that means they're oblate spheroids, which means they bulge slightly at the equator, just as the Earth does because it's spinning, and just as the sun does because it's spinning. So they're not perfect spheres, but they're close to spheres. And they are holes in the sense that they are sinks of matter and energy. So a black hole, defined by its event horizon, the event horizon is essentially not a physical barrier, but it's an information barrier or membrane where information can go in, matter and radiation can go in, but nothing can come out. So in that sense, they are like holes.
The next question is from Interalia 300. Is there an explanation how the slight asymmetry of more matter than energy came about? It appears to be a fundamental part of Big Bang theory, as it allowed for matter to be created.
So physics underlies the equivalence of mass and energy, Einstein's E equals mc squared. And so it is normal in the physical universe for matter and energy to interchange. You can create matter out of pure energy, and you can turn mass into energy. So it goes in both directions. In our universe, it turns out that there are something like a few hundred million, close to a billion photons for every particle, photon, proton, neutron, electron. So the amount of radiation measured as number of photons vastly exceeds the number of particles. And that is presumed to be caused by physics in the very early universe, where there were almost equal numbers of particles and antiparticles. And very early on, in the first fraction of a second, the particles and antiparticles annihilated as the temperature cooled and formed mostly radiation. That's why you have all the photons. And then there was a very small excess or residue of matter, which became all the matter in the universe, 10 to the power 80, along with 80 zeros after it, number of particles. And so therefore about 10 to the 88 or 89 photons.
Excellent. The next question is from an email from John Kingeter, who's asked, has the Earth's volume density or the effective gravity felt on its surface changed over time in a way that has affected the maximum size that animals can grow?
That's an interesting question. So no, the Earth has pretty much been stable since its formation. After it solidified and condensed out of, sort of essentially molten particles and grains of minerals and metals, it hasn't really changed its size potentially, and it hasn't really changed its rotation rate very much, which also might lead to a little centrifugal force and a change in size. So Earth's gravity is more or less the same as when it formed. So the persistence or the ability for large creatures to exist is more a function of biological evolution than it is a function of the constraints of the gravity of the planet. And there have indeed been times when life's creatures were very large. It's called the megafauna era. So 50, 100 million years ago, there were extremely large creatures, the equivalent of which we don't have now. People suspect that some part of it was due to the fact that after the plants took over on the land and a lot of oxygen was being created, the Earth's atmosphere was highly oxygenated. There was a period when the oxygen content in the atmosphere, which is currently 18%, was almost double, about 34, 35%. And that large amount of oxygen for metabolisms that could use the oxygen was able to fuel very large creatures. And so there's a correlation between the composition of the atmosphere and the size of the creatures at some times in the past. Now, nothing, however, to do with the gravity. It's also true, of course, that in the oceans there's natural buoyancy, and so you have always had very large creatures in the oceans because they are essentially immune from the terrestrial gravity of the surface.
Excellent, thank you. The next question is from LZL, who's on with us live. What is the principal difference between astronomy and astrology? How can I emphasize the difference to my high school class?
It's a difficult word confusion because the words are so similar, and there's clear indication in surveys by the National Science Foundation and by our group too that people get confused by the word choice. The basic way to describe it is that astronomy is the science of understanding the universe, its contents, its evolution, its history, and its physical nature. Astrology is a pseudoscience, which is to say it's not a scientifically based idea. It's the idea that the positions of the planets at the time of your birth or afterwards have some correlation with what happens in your life and even your personality. And this idea has been tested. It's not that people just debunk it because it sounds silly. It's been tested and it's been falsified essentially many times in many different studies. It's a fairly harmless belief system. Some people get more annoyed about it than others among my colleagues. But it's certainly been debunked. So you can emphasize to students in a class that while astrology is not scientific and it may be harmless, you learn far more about the universe and about the Earth and even about humans by following the science of astronomy.
The next question is from Dave McKenzie, who sent an email. How were exocomets initially discovered, and can that technology be used to find exomoons?
So exocomets are not firmly discovered, I would say. That's a very tentative detection, because if we think about it, a comet is a tiny object. Comets in the solar system, when they come close to the Earth, are 5 to 10 kilometers across. They're essentially city-sized objects, and they're also very dark unless they're close to a star. And so that's far beyond the capacity of astronomy to detect. Exomoons would be, of course, moon-sized, so smaller than planets, but a lot larger than comets. So it's actually more likely that exomoons will be detected than that exocomets will be detected.
The next question is from Tom Blauvelt, who asks, is it possible that an unknown force experienced sudden decay and that resulted in the end of a singularity, and that might explain why the universe is still expanding? So could there be some unknown force?
So there's speculation about a so-called fifth force in nature. It happens in not just in highly speculative circles, but in conventional theoretical physics circles. Fifth forces are talked about, and that's partly because we don't yet have a complete theory of nature. We don't have a unified theory of the four fundamental forces, and we also don't understand dark energy and dark matter. So fifth forces have been hypothesized from time to time over the past half century, but in the end they have to be subject to experiment. And sometimes these forces are hypothesized to operate on small scales. Gravity is an infinite range force, and the nuclear forces operate deep within an atom on very tiny scales. So often the fifth force that's hypothesized operates on intermediate scales, essentially scales of meters or a lab scale, which means it's subject to lab-type measurement. So there are lab physics experiments underway, and there have been for a decade or more, that are looking for either a deviation of one of the known forces or for a brand new force, and none of those experiments have yet succeeded.
The next question is from Jennifer Branston, who asks, why can't we consider the moon a planet?
Partly because we pretty much know how the moon formed. So the theory of the moon's formation, it is a large moon compared to the planet-sized Earth. So that's fair enough. So the moon obviously rivals Mercury. Pluto is no longer a planet, it's a dwarf planet. So when you have a moon that's that large, it's reasonable to wonder what the distinction is. But in this case, the moon orbits the Earth, and it's substantially smaller than the Earth. And we have a pretty good theory for the fact that it was formed by an impact early in the Earth's history with, say, a Mars-sized object that splashed off some amount of the mantle material that condensed and circularized and formed the moon. So the moon is clearly a satellite of the Earth, and it's not a planet.
The next question is from an email, and there's three questions, but the first two are related, so we'll start there. So the question is, why are stars so far away? And then we'll hit the next question afterwards. So why are stars so far away?
It's a good question. It reflects the way matter condenses in the galaxy. When the galaxy was young, the Milky Way is the collection of stars that includes the sun and its neighbors. And we do know that the distance between stars is trillions of miles, whereas stars themselves are maybe 1 million miles or so across. In other words, the distance between stars is thousands, actually millions of times larger than the star size. And so it's mostly empty space out there. And those distances are large just because the original nebulous cloud that would form the galaxy and all the stars within it was very diffuse. It had a very low density. And gravity formed collapsing objects, and it collapsed them by very large factors. So it took very diffuse material and concentrated it by a large amount into a new object like a star, and evacuated the region around it, thereby leaving a big empty space. And that happened throughout the galaxy.
Excellent. The next question is from an email, or sorry, this is the follow-up to that question is, under what circumstances do two dead stars collide with each other?
It's unusual for dead stars to collide with each other, but when it happens, it's a very interesting phenomenon. It's unusual because the distance between stars is so great, as the first question alluded to. However, stars do not always form singly. Most stars in the Milky Way are in binary, triple, or multiple systems. So isolated single stars like the Sun are actually a minority. And given that stars form in pairs or groups, they are much closer together. They're orbiting each other, and over time, those orbits can decay and the objects can collide. Now, for two dead stars to collide, that requires that they have ages where they've both gone through their stellar evolution and both ended up as stellar remnants. And so the stellar remnants would be white dwarfs, neutron stars, or black holes. The neutron star category is particularly interesting because just in the last 4 or 5 years, we've learned that the source of most of the heavy elements in the universe, most of the gold, silver, platinum, precious metals, uranium, all the heavy elements in the universe come from colliding neutron stars. In other words, star corpse collisions that release a lot of gravitational waves and create enormous energy for generating heavy elements. So even though dead star collisions are rare, when they do happen, they are spectacular phenomena that are of great importance in the universe.
Excellent. The final question from this group of them is, can you talk about some things that are absolutes in the physical world? What things are absolute or that we know are absolutes?
Some of the things that we know are absolute are the absolute zero. That's a good place to start. There is a zero of temperature. There's a hypothetical temperature at which there is no motion of any of the particles, and that's an absolute. You can't go lower than absolute zero temperature, no energy, no motion. Other absolutes are the constants of nature, which is like the gravitational constant, the fine structure constant. These physical constants appear not to have changed. People have done experiments to look for their changes with location in the universe over cosmic time and haven't detected that. So these fundamental constants of nature do also seem to be absolutes. But there's not a lot that's absolute otherwise. Space and time are not absolute because general relativity connects them and allows them to change. Particles are not absolute because most of them can transform into energy and then go back again. And then many particles actually decay, possibly even the proton itself. Normal matter may decay if you wait long enough. So it actually turns out that in physics and in the physical universe, there are only a handful of absolutes.
Excellent. The next question. So we've got a series of 3 questions that are all kind of related to each other. So we'll kind of cover those together. For those of you who are interested in pursuing astronomy as a career or learning more about astronomy, we have covered that before. So we tend to not do that every session because we get people interested in that every session. But we've covered it so many times by this point that I recommend that you go check out some of our previous live sessions if that's something that you're interested in looking into the answers to more deeply. But generally, a couple of people would like to know how they can develop their knowledge of astronomy and astrophysics.
Taking an online class like the ones we offer through Udemy and Coursera, that's obviously a good way to do it because you can do it on your own timeline. The courses are free. It's very flexible. It's video lectures mostly, and so you can do it on a handheld device too. So I think that's a pretty good way to learn quite a lot of astronomy. Obviously books are another way. There are textbooks in astronomy tend to be a little bit dry, and then beyond the introductory level they can be fairly mathematical. But there are popular books on astronomy. Every year there are dozens of popular books that tend to be on particular topics like cosmology or the search for life in the universe, or dark matter and dark energy and so on, particular topics, or black holes. And the ones that are well written and well reviewed, you can just look at the ratings on Amazon or Google, are very good ways to learn astronomy because you're in the hands of an expert who's writing at a popular level, and so it's very digestible. There are also magazines, which are print magazines but also have online versions, like Astronomy and Sky and Telescope. These are more for amateur astronomers, but they all include monthly or period pieces about particular topics in astronomy written at a popular level. And then other magazines like Scientific American feature astronomy pretty much every month, and they're always well-written articles.
And then somebody else, Drutiman, asks if you could just recommend a couple of books that you think are good ways to know more about space and astronomy.
Sure. Well, I'll push one of my own books to start. I wrote one about black holes called Einstein's Monsters a few years ago, so if you were interested in black holes, that's a good place to start. Neil deGrasse Tyson has had a series of books. Often they're short pieces or short chapters where the topics hop around, so you can cover a lot of ground, and those are good. There's a couple of books written by Phil Platt, who's known as the Bad Astronomer. He had a blog that's been very successful for a number of years, and his books are well written and cover a range of topics like impacts on the Earth and threats from space and so on. So there are dozens of people writing good popular astronomy books.
Excellent. The next question is from, I believe it's Amir. Do we have any good explanation and candidates for particles that would show us evaporation of primordial black holes? Or do we have any ideas about how we might detect the evaporation of these primordial black holes that may or may not have existed?
So primordial black hole is a hypothesis that in the early universe the density was such and the sort of fluctuations of space-time were such that you could generate small microscopic black holes. Now by microscopic I mean they're masses that are well under a gram, like a microgram or a picogram. So they're far, far smaller than collapsed stellar objects. And these would have emerged early in the universe, and most of them would have evaporated by now, according to Stephen Hawking. The Hawking radiation is how black holes disappear. And these little black holes would have an evaporation time that's less than the age of the universe to this point, and so they should have disappeared. Now that's pretty difficult to detect, however, because the radiation that they emit is kind of feeble, and it's not localized in space. These would have been throughout space, and the universe is full of radiation in other ways, especially from the Big Bang itself and then from all the generations of stars that have been created. So the signatures of primordial black holes are extremely difficult to determine, to measure, and even to understand, because the theories are not that mature. So this is not an area that's moved forward very far, although the window on possible primordial black holes has gradually closed. So the mass window has closed somewhat, in the sense that the very small ones would have disappeared so long ago they would have no effect on the universe, and the very massive ones would still be black holes. So we're not looking at their radiation.
The next question is from Anthony Moore, who asks, can you please give a brief description of or explanation of a Feynman diagram?
Sure. A Feynman diagram was a mechanism developed by Richard Feynman, famous Nobel Prize-winning physicist who worked at Caltech. And I think he first developed it in the 1950s, but it was being written into textbooks by the 1960s. A Feynman diagram is a way of visualizing the interactions between particles and radiation. And so you essentially have an interaction where a particle A and particle B interact, and their interaction is often mediated by other particles or by photons. And these interactions and mediations can be very complex because it's not a single interaction and then particles A and B just leave the scene. Sometimes the particles are transformed in the interaction, or new particles are created. And so Feynman diagrams are ways of encapsulating the various possibilities that can happen when two particles interact. Where radiation is exchanged, particles may be exchanged or created or destroyed. So these diagrams can be quite complex, even for simple situations. And it's a very powerful visualization technique, but it's also a way the physicists use to frame their calculations of what happens in these interactions.
The next question is from Wendy, who sent an email. Since certain chemical elements can result from abiotic processes as well as biotic, what would definitively be an indication of life somewhere other than Earth?
It's a good question. So the idea of the biomarker or the biosignature, which is something, a chemical signature of life, the idea of something that uniquely indicates life and couldn't represent anything else, that's been somewhat elusive. And I don't think astrobiologists would claim that they have a single signature that would do that. Typically, a classic biosignature is oxygen in the atmosphere of a planet, a terrestrial planet, because the atmosphere in the Earth that we breathe, 18% of our atmosphere, was produced by microbes a few billion years ago. So it indicates a metabolism at work. If you see a high oxygen concentration in the atmosphere of a terrestrial planet, it's a very strong indication of biology. But geologists have come up with ways of generating a lot of oxygen, maybe 6 or even 8% or 10%, but not 18%, just abiotically, without biology. So astrobiologists are being very cautious about saying, well, this has to be biology beyond some level, because we don't know the range of geological processes that could generate a biomarker. Phosphine is another example. It's been seen in very trace quantities in the Venusian atmosphere, and it was a flurry of news stories a few years ago that that was a biomarker, that there might be life in the Venusian atmosphere. There's a very small concentration, and any time a chemical is at that level of concentration, then people will be creative and they'll figure out abiotic ways to get that chemical as well. So unfortunately the answer is there's no compelling single biomarker. What is going to win the day in the future for detecting life beyond Earth in the atmosphere of an exoplanet is a suite of chemical signatures which, taken together with a model for the atmosphere, indicate that there must be biology driving that chemistry. And so that can include a variety of things like oxygen, ozone, methane, water vapor, and so on. And there's astrobiologists working hard on this problem.
The next question is from Karim, who asks, how does space-time deform and retain information about mass without a medium linking local deformation to creating some kind of overall global deformation? Or is this curvature just a mathematical abstraction?
Well, it is a mathematical abstraction, but it is also a physical mechanism whereby mass and energy curve space and time. The mass and energy are hyphenated because they can convert one to the other, and the space and time are hyphenated because space-time is a mathematical construct of general relativity. So the curvature of general relativity, that's how the gravity theory is expressed, applies both locally and globally. So you can have a high concentration of mass energy locally, which will distort space-time and lead to the deflection of light, gravitational lensing, and so on. Or you can have a global curvature of a cosmic space-time, an entire universe, where there's curvature of the universe and light and radiation flowing through the universe is deflected and lensed and focused. So both things are true at once. So your physical theory is explaining all scales with the same mechanism.
The next question is from Faisal, who asks, the percentage of the visible universe is 5% and the percentage of dark matter is 26.8%. Is it possible for this percentage to change or this ratio to change?
Well, these are the present day numbers that we measure, and it's indeed the case that dark matter outweighs normal matter by roughly a factor of 5. Now, as the universe evolves, the dark matter is diluting, and the normal matter too, because the universe is getting larger, but the amount of matter, dark or normal, is fixed. And so, whereas dark energy is increasing, because dark energy is driving the cosmic accelerated expansion, and the dark energy in any volume of space is constant. So in that sense, in the pie chart of what the universe is made of, the fraction that is dark energy is going to be increasing into the future, and the fraction that's dark matter or normal matter will be decreasing. So this is just one snapshot in time.
The next question is from Abhishek, who asks, when scientists first discovered the Higgs boson, how did they realize that it's a boson, and how did they distinguish this boson from another boson?
So the boson description, which is the naming of bosons and fermions. Bosons are integer spin subatomic particles, and fermions are half-integer spin subatomic particles. These refer to Subrayendra Bose, an Indian physicist in the early 20th century, and Enrico Fermi, the famous American-Italian physicist in the mid-20th century. So bosons are integer spin particles, and so that's the first part of the signature, that in a high energy physics experiment you can measure what the spin of a subatomic particle is by the way that it interacts with other particles and by measuring its magnetic moment and various other tools. So you know that you're looking at a boson, integer spin particle, and then the reason you think you're looking at the Higgs boson or the Higgs mechanism and how it's exerted is because of the energy. And so the energy at which a resonance was seen at CERN, the high energy physics lab, in 2012 and 2013 was at about 130 GeV, giga electron volts. And that particular energy, that resonance at a particular energy, matched the theory and the expectation for the Higgs particle. And so that's how they knew they'd found it.
The next question is from Arif, who asks, how does or how could synthetic biology or cyborg technology change space exploration in the future?
Well, I think it's a fair bet to say that space exploration will be dominated by cyborgs or robotic technologies, simply because humans are frail. The costs of building rockets for them and keeping them alive and sending them large distances are prohibitive. It's essentially ruled out that we are ever going to explore in any feasible time frame beyond the solar system with humans. And even within the solar system, it's far easier done with robotic technology. So basically at the level of the convergence between robotic spacecraft, the kind of which we've seen around the solar system, the little rovers on Mars and so on, and AI-driven media which allow for exploration with the thought process going on in a computer that's doing the exploring and the results are conveyed back to Earth, that's going to be the way things are done in the future. This technology can be miniaturized, of course. This technology is robust and can travel in the vacuum of space through high energy radiation fields that would kill normal people or compromise their health. And so there's no question that cybernetic or robotic or AI-driven technologies will be the way space is explored in the future.
The next question is from Hernan Reyes, who asks, in one of your writings in Frontiers of Astrobiology, you quote Arthur C. Clarke, who says that any sufficiently advanced technology will be indistinguishable from magic, which argues that signals that we might actually detect and recognize as the hallmark of a technological civilization will be those that are deliberately broadcast for the benefit of emerging technologies. Could you elaborate a little bit on what this means? Because to me it seems like that unless higher order civilizations are condescending towards us and beam out what are to them like obsolete radio messages, there's little chance of us being able to identify vastly superior technology.
I think that's right. I think the problem is a technological mismatch that's likely to be the case between civilizations at different stages of development. All you have to do is look at the fact that we've only had radio communications and space travel for less than a century and computers to realize that there would be no way to communicate with humans through most of their history without those technologies. And as for the future, we simply don't know. You could argue that sending electromagnetic waves, radio waves, or pulsed lasers is one way to do it, but it's fairly primitive. These signals attenuate with distance by the inverse square law. The light is absorbed by dust and can't travel very far through the galaxy. Another way to go would be to create gravitational waves, something we've just learned how to detect in the last decade. But if you had the ability to manipulate matter such as to produce gravitational waves, then you could communicate, you can encode information in them and communicate with them. And these waves dilute much slower with distance. They travel through all media and they could be registered by an advanced civilization. So gravity waves or neutrinos or other modes of communication are hypothetical and not unreasonable, but just beyond our means at the moment. And that's the Arthur C. Clarke point. I think he's just saying that technology changing exponentially quickly means it's essentially impossible to project what our technology will be able to do in a few hundred years. And something that's that advanced does indeed seem like magic, as radio transmitters and lasers would be magic if you took them back to our prehistoric ancestors roaming in the plains of Africa.
The next question is from definitely not Kate Roblox. If we find an exoplanet that is likely to support life, how could we travel millions of light years, or any light years, to study it? Is there any progress regarding methods to reach those faraway exoplanets?
No, it's a very difficult problem. So we're stuck with remote sensing. We're essentially using the light that we receive from these planets that are light years away because we are not able to travel those distances. There is the Breakthrough Starshot project, which is aiming to send fleets of nanobots to Proxima Centauri, the nearest star system, just over 4 light years away, and accelerating with solar sails and sort of beamed microwave radiation, accelerating those little spacecraft to 5 or 10% of the speed of light, gets you there in 30 or 40 years. So that's a generational time scale, but it's not a crazy time scale. And that's just to the very nearest star. To go to any beyond the nearest star is really implausible, even with the miniaturized robotic spacecraft. So I think essentially in this field, the field of exoplanets, and especially the ones that might have life on them, we're dealing with remote sensing.
The next question from Maxwell Bennett. I don't remember exactly what this is in reference to, but you were talking about, I think, maybe gravity being a long-range force. But wouldn't that mean that that planets could affect Earth, and then that would be like in favor, or supporting the idea of astrology? Can you just separate that confusion between, gravity not affecting Earth from these faraway planets, but then also it being a long-range force?
Right. So it's a long-range force, but it's an inverse square force. So it goes down, the strength of gravity goes down by the inverse of the square of the distance, and that's quite a rapid diminution. So once you're far from a large object, the gravity from that object is very weak. And the way to put that is, if you're reading a book, the gravity of the book on you is stronger than the gravity of any of the planets in the solar system on you. So that's immediately saying that if astrology is trying to base itself on gravity and its effect of the planets on individual people, that's a completely implausible mechanism.
The next question is from Carla. Is there any chance that we could send a probe to Venus to study its atmosphere again, now that new discoveries of elements and substances have been made?
Yes, there is, and it's planned. So Venus has sort of been the Cinderella planet, according to many planetary scientists. I'm not a planetary scientist, but I talk to my colleagues, and they feel that Mars has been getting all the love, getting all the attention, getting all the rovers. And that makes sense in some way because it is also our nearest neighbor, almost our nearest neighbor, and there's the likelihood that life could exist even now under the surface. Venus does not seem to be as favorable for life. But in the last couple of years, NASA has had some competitions for new space probes, and I think 2 so far have been approved at the Phase B level, which means they move forward with a few tens of millions of dollars of development money. And these are going to be, one of them, I think it will actually be a lander, so it's designed to land on the surface and survive more than the sort of 20 or 30 minutes that the Venusa Russian lander survived in the 1960s, and transmit a lot of data as well as down through the atmosphere. And then there's another mission that's more of an orbital mission, but will sample the outer atmosphere and measure deep into it. Now both of those missions so far have had a green light. NASA's got some budgetary problems, so we can't be sure they'll both go forward. And if they do go forward, it probably will be not for 6 or 7 years.
The next question is from Joao Barbosa, who asks, if humankind has the wish to live on Mars in the future, how would we be able to handle the lower gravity, and how would that affect us?
So the gravity on Mars is not dramatically lower, so 40% gravity is not an unreasonable amount. It's not nearly as difficult to adapt to as zero gravity, which is what astronauts in the space station, some of whom were up there for years, had to adapt to and really suffered health consequences from. The best guess is that 40% gravity or Mars gravity will not be too detrimental to humans for some limited period of time. And then also, of course, people who will be in this environment will use resistance exercise training to maintain their muscle mass and so on. So there are various strategies they'll have to use. So certainly the gravity is survivable. The atmosphere, of course, is almost non-existent, so anyone who's there will have to be living in a bubble dome or an underground facility, maybe in one of the lava tubes that's been found in the last few years. And they will also, of course, have to be protected from the ultraviolet radiation that pours in unimpeded because Mars' atmosphere is so thin.
American Utility, who's on with us live, asks, you use the term information in regards to black holes. Can you explain a little bit more about what that means in astronomy?
Yes, information is a term really out of computer science or information theory. Claude Shannon in the 1940s developed the definition in a fundamental sense about information. In terms of a black hole, information represents, for example, what constitutes the black hole. So the black hole's parameters are very few. It has a mass, it has a size, it has an angular momentum, and that's about it. And it has a temperature implied by Hawking radiation and the evaporation. But the information of a black hole potentially is the information of all the things that went into it, like what it's made of. And the loss of that information in the black hole is what leads to what's been called the information paradox. So information is, the number of ways of describing a physical system that needs more descriptors or more parameters to describe it contains or holds more information than a different system.
The next question is from Thritiman, who asks, does antimatter exist?
Yes, it exists. We see antimatter routinely. It happens spontaneously when energy turns into particle-antiparticle pairs, and we can detect that in the lab. It happens definitely in high-energy accelerators, which create collisions where the energy can go into antiparticles, and those antiparticles eventually disappear. They don't last for long, but we definitely can create them. But it's very fleeting because there's so much matter, and an antimatter will annihilate immediately on contact with matter that it will never last long. However, with very great ingenuity, antiprotons have been created in significant numbers, I think a few hundred, and even an anti-hydrogen atom where you've paired an antiproton with a positron and got them to stay together long enough to create a single atom of anti-hydrogen. So that these very clever high-energy experiments have been able to create tiny amounts of antimatter at enormous cost. If you had to put a price tag on antimatter, it's, I think, quadrillions of dollars per gram. So it's the most expensive material conceivable.
The next question is from Arif. Are there any guidelines to make a constitution or laws for other habitable planets? So let's say humans travel to, we could even say the moon or inhabit another planet. Are there any rules for how laws or constitutions or governments would be set up?
No, there are no international rules. Space is really the Wild West. There's only been 2 UN treaties that apply to space. The Outer Space Treaty of 1965, which banned weapons in space, a very valuable thing to do in the time of the Cold War. And then the Moon Treaty of 1979, which talked about governments not being able to own objects in space, but of course said nothing about private individuals or companies, so leaves us hanging on that issue. Those are the only international treaties that have teeth because the UN has almost all the countries in the world as member states. For generally, there are no rules. There are informal agreements between space agencies as to their operating procedures, and NASA's partners in Europe and Japan and elsewhere have agreed that contaminating foreign or alien objects is a bad thing. And so there are protocols for decontaminating or sterilizing spacecraft if they go to, say, Mars. and just not gratuitously contaminating another object. But these are not binding by any national or supranational body, and so these are just sort of tacit agreements of space agencies. Private space companies have no such constraints and no such agreements, and they're operating, on their own principles.
The next question is from Maria, who asks, is there a logical way to explain four-dimensional space? And is it possible that the universe belongs to the realm of four-dimensional space?
So there are possible extra dimensions of space. Remember, general relativity is a four-dimensional theory involving three dimensions of space and one of time that's coupled to the three dimensions of space. But you can also generate higher dimensional space constructs, and these are, in high energy physics, these are called brane theories, where brane is a contraction of membrane, and where membrane is a description of a two-dimensional surface that might be embedded in a higher dimensional space. So mathematically, you can conceive of four-dimensional space as 5, 6, 7, 8, as many as you want, actually. And the question only is whether these are physically manifested in the universe. And at the moment, we haven't seen any sign that they are. String theory obviously posits that there are higher dimensions, 10 or 11 dimensions of space, where most of them are compactified on very small scales and could only be accessed at extremely high energies. But there's no experimental evidence for that. So at the moment, the best and most robust and mature theory is the three dimensions of space plus one of time of general relativity.
Dan Cooper would like to know, how serious are the problems with the Boeing rocket that has stranded 2 astronauts on the International Space Station?
Yeah, this is a developing story, and it seems quite serious. NASA's wanted to hedge its bets. It does not want to depend fully on SpaceX for delivering supplies and astronauts to Earth orbit and to the space station. The price NASA's had to pay for not depending on SpaceX is that they're partnering with Boeing on a Starship that has been tens of billions of dollars over budget and not just years but decades behind schedule. So it's awkward because the Boeing Starliner has got some serious problems, and it's been leaked in the press in the last few days that even within NASA there's serious disagreement as to whether the astronauts are safe in the Starliner, and NASA's hedging its bets. It's trying to play this out for another 6 or 8 months. So people who went up for what they thought was an 8-day visit, it's going to be at least 8 months, and it may be a year, and it's all because of Starliner's problems. And these problems have been baked into a development process that's long-standing, and oversight probably by NASA that was inadequate. And maybe what we may be seeing here is a reflection of the culture at Boeing that's led to problems in the aviation industry too, the blowing out of door panels and so on. So it's a tough situation because lives are on the line. Astronauts risk their lives when they go into space, and 14 died in 2 shuttle disasters, and NASA obviously doesn't want to lose anyone else in a Boeing Starliner. But at the moment, I'd say all bets are off. They simply don't know how to fix all the problems.
All right, we have time for one final question, and then we're going to wrap it up. Luap605, who's on with us live, asks, the Perseid meteor shower is this weekend. What is the typical size of meteors that we will see in the night sky, and how big do they need to be to survive burning up and landing on the Earth?
So the Perseids is a good meteor shower. Remember that the debris field through which the Earth passes that gives rise to the meteor showers, each of the famous named meteor showers represents the debris trail of a comet strewn along its orbit, where the Earth passes through that debris at a particular time every year, the same time. But the density of the debris and its variation in size is highly unpredictable, and that's why meteor showers are unpredictable from year to year. The things that we call shooting stars, or call colloquially shooting stars, are typically grain of sand sized objects moving at 10 or 20,000 miles per hour. So even that small, when they burn up, they deposit a lot of kinetic energy as they vaporize, and so they light up in the atmosphere. So that's what you see when you see a shooting star or from the meteor shower. To get to the surface, typically something has to be much bigger. It's a golf ball, tennis ball, football sized. So the really small ones, which cause most of the light show, are really tiny, and they're really burning up very high in the atmosphere. And a tiny, tiny fraction of all the incoming particles are big enough to survive passage through the atmosphere and land as meteors. Thanks for all the questions. Good variety as always. And to Matthew for facilitating. I guess we're on for in another 3 weeks from now. We'll be back with you again.
That's correct. On August 28th, we will be back again. For those of you who are still here, if you could hit the like button, that would help us out, get these live sessions out to more people, and subscribe if possible to our channel. Then the other thing I wanted to mention is there's somebody on here who had questions about the course. For questions about our Coursera courses, you really need to contact Coursera directly to ask questions about the grading and things like that. We just don't have any control over that and how it works. If you really need to ask us a direct question, there's the email address at the top of this discussion, this chat thread. So thank you all so much for joining us today. We will see you in 3 weeks, and have a good rest of your week and weekend. Take care, everyone.